simulating and downloading counters to FPGA boards with TinaCloud, using TinaCloud's schematic editor. In our previous videos listed on the screen, we have shown how to create a simple combinational digital circuit, and download it to an FPGA board in TinaCloud using schematic symbols, VHDL or Verilog. Now, in this tutorial video, our circuits are counters. The counter is a widely used sequential logic, where the output depends on the sequence of past inputs, and a present value of the input signals. In the case of a counter, the input signal is the clock, and the output's value represents a number. The counter circuit is usually built up with flip-flops. Now let's see our first example, a binary up counter. Start TinaCloud. Then open the binary counter.tsc file from the Tina examples/fpga/counter folder. The counter is constructed from 4 rising edge sensitive D flip-flops, counting from 0 to 15. Flip-flops store the count until the next event, when the clock signal produces a low to high transition. The least significant bit is QA. The clock source is 1 Hz for good interactivity. Following the practice, we assign a short clear pulse by PS at the very beginning before the counting sequence to reset the flip-flops. The full name of the circuit is asynchronous binary up counter. Asynchronous because each flip-flop has a distinctive clock, usually from the previous stage. Now press the transient interactive button. Let's examine the circuit operation. When the clock is changing low to high, the indicator turns red. Then, the least significant flip-flop, U1, will toggle, and this effect propagates through each flip-flop. This ripple phenomenon causes a delay in the nanosecond domain, but if we don't care about an immediate result, short transients are acceptable. Now, before testing our circuit in a real FPGA environment, we need to extend our schematic with FPGA pin connectors as we have shown in our previous video. We will use a Xilinx Basis 3 FPGA board. We shouldn't forget what resources our FPGA board offers. Regarding the Basis 3 board, we should note that such a board has only one clock generator with 100 MHz output frequency. Now, click CLK1, then in the Properties window enter 100 MHz in the frequency field. Then click OK. Since the board doesn't provide a 1 Hz clock, we have to apply a prescaler, which will produce that from the Basis 3 100 MHz oscillator. Now, let's insert this prescaler as a macro, which has been written in VHDL. Select Insert Global Macro from the Insert menu denoted by a green plus sign. Then, in the Global Macros dialog, select the prescaler and click OK. Place the macro on the workspace, then, pan the circuit by holding down the left mouse button while moving the mouse. Now, you can attach the macro to the input of the circuit, so that the clock frequency will be divided at the input of the counter. The prescaler macro has one input, named CLK, and one output, named PCLK. The clock frequency at CLK input is 100 MHz, and it is 1 Hz at the PCLK output. To see the code, double-click the macro. Then, in the Properties window, click the 3 dots at the end of the HDL code field. Now, close the dialogues. The prescaler itself is also a counter. When the counter reaches 50 million, the PCLK output is toggled, so that the frequency of the clock at this output is 1 Hz. This is an additional logic to reach slow, human-readable operation speed. Now, add the FPGA pin connectors to the circuit as shown next. Select the first FPGA pin from the special toolbar, then connect it to the clock input of the circuit, before the prescaler macro. Next, double-click the pin connector, then, in the Properties window, click the 3 dots at the end of the pin settings field. In the Device section, click the Xilinx Basis 3 Arctic 7 FPGA trainer board. Then, select Clock under the Group section and CLK under the Pin section. Click OK to accept the settings. Rename the label of pin 1 as CLK as well, and click OK. Now, insert the FPGA pin connectors for the 4 outputs of the circuit, and assign them to the LEDs. LED 0, LED 1, LED 2, and LED 3. Set the LED names to LED 0, LED 1, LED 2, and LED 3 respectively. Finally, remove the pulse source and connect the clear input of the flip-flops to logic high. The flip-flops will be initialized by the FPGA automatically. Before generating the source files for Xilinx Vivado, save the file under the name binary counter pclksynth.tsc in the My Circuits folder under your account. Click the T&M menu and select Export to Xilinx tool. Then click Xilinx Vivado. Next, open and extract the binary counter pclksynth Xilinx export.zip file. Create a folder. We will name our folder Designs, then copy the files, including the VHDL and XDC files into this empty folder. To produce downloadable content, first we create the Vivado project. Start Vivado. Then click Create Project. Click Next. Enter the project name, in our case, binary counter pclksynth. Then click Next. Click Next again. Then click Add Files. From the Designs folder, select the VHD files as source file. Then click OK. Click Next again. Click Add Files again to add the binary counter pclksynth.xdc file as well. Select the file, then click OK. Click Next again. To finish project configuration, select Boards in the Default Part dialog. Select Bases 3, then click Next. Click Finish. Now, Vivado is initializing our project. Click Generate Bitstream to produce configuration data for the FPGA. Then click OK in the Launch Runs dialog. Now connect Bases 3 via USB with the Vivado machine and turn the board on. As soon as the bitstream generation successfully completed message appears, select Open Hardware Manager, then click OK. Next, click Open Target, then select Auto Connect. Let's finish programming the hardware. Select Program Device, then in the Program Device window, click the Program button. You will see the FPGA is programmed message, and the counter lights come up counting up in binary. If the output code reaches the maximum value of 15, the counter next state will be 0. The simulation of this circuit must be handled with care, because the prescaler has to count to a very large number. Before the output toggles, we have to slow down this module. Therefore, in the simulation, change the input clock frequency to 100 Hz and change the macro code so that the counter counts up to 50 instead of 50 million. This way, we will have a 1 Hz clock coming out of the prescaler for the simulator. Press the TR button to start the simulation. Save this file under the name binary counter pclksynth.tsc. A counter can count not only a series of pulses, but other events too. For example, the number of times a push button has been pressed. To demonstrate this, let's go back to our original circuit. Open the binary counter.tsc. Now, replace the clock source with a push button. Delete the clock source, then select a push button from the switches toolbar. Let the push button PB generate a high level when it is pressed, and a low level when it is at rest. The low level needs a resistor. Place one from the basic toolbar. Thus, it will work the same way as the button does on the Bases 3 board. Start transient interactive analysis by pressing the TR button. Then click the push button, PB, to step the counter. When the button is pressed, a rising edge occurs on the clock input of the first flip-flop, and the counter outputs will produce the next binary code. Stop the interactive analysis. Before implementing this circuit on an FPGA, save the file under the name binarycounterbtn.tsc. Here we note that the mechanical switches and push buttons have contact bouncing problems. If we press a button once in the real world, that may generate a series of pulses. That's why we place a contact debouncing VHDL macro at the counter input. Before we do that, remove the push button and the resistor. These are not necessary because they are on the board and don't belong to the synthesizable logic. Remove the pulse source as well. The FPGA will take care of resetting the flip-flops. Now, let's insert the macro, named debouncer, which has two inputs, CLK and PB, and two outputs, PB down and PB up. CLK is connected to the base's 3 clock port, and PB is connected to the center push button, BTNC, of the board. Output, PB down, is connected to the clock input of the first counter flip-flop. Click the Insert menu, then select Insert Global Macro. Select the debouncer, then click OK. Place a clock from the source's toolbar. Change its frequency to 100 MHz and rename its label as clock. Then connect it to the debouncer macro. The debouncer will eliminate the unwanted glitches by resampling the button's signal with a low frequency and constructing a single pulse when the button is pressed or released. Select two FPGA pins, then place them as shown next. Double-click pin 1 and set its parameter as follows. Rename its label as well, and click OK. For pin 2, select buttons under the group section, then BTNC, and click OK. Rename its label as well. Place 4 more pin connectors and connect them to the logic indicators, QA, QB, QC, QD. Set their parameters and rename them as we did previously. Since we will not need the logic indicators, we can delete them. Now, the circuit is ready for the export of Xilinx Vivado. Save it under the name binarycounterbtnsynth.tsc. Let's generate the source file for Xilinx Vivado.
Now connect Basis 3 via USB with the Vivado machine and turn the board on.
Here, every time the center push button is pressed, a pulse is sent to the counter, and as a result, it counts up by 1.
For more information, visit our website, www.tinacloud.com. Visit our YouTube channel, www.youtube.com/tinacloud. user/Tina Design Suite.